in this, I guess we got. So, hello everybody. As I just said earlier, my name is Hardik, and we will be talking about stability analysis, bifurcation theory, and its applications. So, uh, can you see the next slide, by the way, where it says contents?
Yes.
Okay. So we will first be talking about flows in a one dimension with one variable. And then we talk ability and the definition. And then we will go on to one variable bifurcation theory, which we talk about what's the definition of bifurcations, and we will talk about two different types of bifurcations. After that, we move on to two variable systems instead of one. And finally, we will just look at a biological application of what we've learned so far. So consider a dynamical system described by such a variable x over time, like x at t is a function of time. Then the rate of change dx by dt is often represented in Newton notations, such as just x dot, which is dx by dt, and found from the ordinary differential equation described the system. So I hope everyone here is comfortable with ODEs. So recall that the capital F, which is a function based upon the first derivative of time, x, and t, which equals 0, is just a general representation of a first order differential equation. Then afterwards, x dot, if it's just equal to a function of f of x and t, two variables, that is just a first order ODE in an explicit form. If, let's say, x dot is just equal to f of x only, and there is no t explicitly written, then this is also known as an autonomous first order differential equation. So no explicit dependence on time on the right side. It's just x. And let's say if we just look at example where, of course, x dot is equal to ax plus b. This is just a linear autonomous first order differential equation where a and b are both constants. So solutions to such an equation, x dot equals f of x t, are of the form x dot equals f of x, which is also a function of time as well. Then therefore there exists a family of solutions also known as integral curves, trajectories, or orbits. In order to specify a solution, we of course must have an initial condition x naught at time 0. So therefore, we can see what integral curves look like in the next slide. As you can see here from this diagram. Of course, monotonic solutions, which means something that is going either only increasing like this, or it'll be decreasing like this. And then the right panel shows that there are non-monotonic because it's going up and down, has different slopes while crossing the dashed horizontal line. And we will find out that these type of non-monotonic solutions do not exist. So yes, like what you see here, when x dot is greater than 0, it's increasing and it's flowing in the direction of the x-axis. And when it's less than 0, like here, it's going away from the x-axis. And of course, non-monotonic, since it's going up and down, therefore they have different slopes for the same value of x. And then this means that if solutions exist, you have two solutions that cross, which is obviously not true because they have to be unique. So now we will look at a few definitions. Therefore, we will look at what a phase portrait is. So solutions are called orbits, and a collection of all such orbits are known as a phase portrait. For example, the horizontal axis with arrows, which we will see in the next figure, is called the phase line. Now, important solutions such as the x or t, which are just a constant, are just known as stationary solutions, which are also known as equilibrium points. Of course, when the x of t is just a constant, then obviously differentiating it, which means x dot, differentiate in terms of time, would just mean that x dot equals 0. Therefore, f of x, as what we've defined, will also equal 0. And therefore, equilibrium points are always the roots to satisfy x dot equals 0. Now, what we said earlier, trajectories cannot cross the equilibrium points, and therefore they divide the x-axis into domains where situations behave differently, which is why they are obviously they are monotonic. Function f of x is equal to 0 in equilibrium points, while they have a certain sign between neighboring equilibriums. So let's say if this point is f of x is equal to 0, then if we find another f of x which is greater than 0, then the solution of x is increasing. And if the point f of x is less than 0, therefore it's decreasing. And yes, the type of analysis based upon this type is called qualitative analysis. This is, of course, illustrated in the next figure. And then the stability of the equilibrium points is defined the same way as the stability of fixed points for maps. There should exist some neighborhood of equilibrium points such that the orbits originated in the neighborhood do not diverge from equilibrium. More formally, for the proper definition, if x star is an equilibrium point and there exists epsilon such that for all x with the initial condition of x naught, in the range x naught minus x star, the equilibrium point is less than epsilon, the solution as the x goes to its equilibrium point as t goes to infinity. Thus, x star is an asymptotically stable equilibrium point. And therefore, the collection of all values such that x of t is going to x star is also known as a basin of attraction of an equilibrium point x star. So therefore, we can see in the figure right here, where it's a graphical analysis of, let's say, x dot equals f of x, plotting x against f of x. So therefore, when you equal this to 0, it has 4 roots. You can see x1, 2, 3, and 4. And just by the diagram, just looking at it, we can see that it's increasing for f of x is equal to 0 between basically between x2 and x3 and greater on and x4 where it's all positive. And when f of x is less than 0, where you see the negative, it's between x1, x2, x3, and x4. So therefore, the x2 and x4 are actually unstable since the orbits diverge from them. We will talk about stability later on in the slides. We can obviously just look at the derivative, positive, positive, so they will go away. We will see the definition and why x3 and x1 converge. So let's just look at a very simple example, just a linear equation of x dot equals a of x. So just finding the solution, we just separate the variables. X dot equals ax, obviously rewriting it as an ordinary differential equation and separating the variables. And then we can integrate this to find that ln of x equals at plus c, which therefore x is equal to e to the power c times e to the power at, or we can, since e to the power c is just a constant, we can just replace this by a. So if x of t is equal to y naught, let's say if that's the initial condition, then x naught which is also by definition an initial condition as well, equals a times e to the power 0 because time is 0, which therefore means y naught is equal to a. So a right here is the initial condition. Thus the solution x equals x naught. Again, x naught and y naught are exactly the same as I've just written it as such. Xt equals x naught times e to the power a of t. And therefore, if a, let's say, is less than 0, then x of t, of course, will be going to 0 as t goes to infinity, because obviously that'd be e to the minus, let's say, infinity, which would, of course, converge to 0. And if a is positive, it will diverge. As yes, it can go to either plus or minus infinity, depending on the sign of x naught. So we look at another theorem where the equilibrium point x star is asymptotically stable if f prime of x is less than 0 and unstable if it's greater than 0. So let's say we make a substitution where x of t equals x star plus epsilon, where epsilon is now a variable of time, and it's the difference between x and x star. So therefore, if we do a linear Taylor approximation from this and substituting, then therefore we of course get x of t equals d by dt, x star plus epsilon. But x star is obviously a constant, so because by definition of derivatives, you can just separate this. So this will be 0, and it will just be x dot of t will equal e dot. Now, of course, x dot is equal to f of x by definition. So if you just substitute that in, f of x equals x star plus epsilon, and then we do a Taylor approximation, which is just only considering linear terms, f of x star plus f dash of x star e. But since we know that this is a stability point, so this point right here will be 0. Therefore, it's just f prime of x star e. And thus, we find at the end that e dot is just equal to f prime x star times e. But since f dash of x star is a constant, therefore we can just integrate as what we've seen before to get e of t equals epsilon naught e to the power of f prime x star times t. And you can just look at this and realize as t goes to infinity, if f star of x is negative, epsilon will go to 0, hence x of t will go to x star. Likewise, if f prime of x star is positive, as t goes to infinity, the epsilon dot goes to infinity, and therefore x star would not, x of t will not converge to x star, it will diverge. Is what I've basically just said right now. So thus, if let's say it converges, meaning the f prime of x1, which is one equilibrium point, is less than 0, then that equilibrium point x star is asymptotically stable. And similarly, we can just show that if x prime of x1 is greater than 0, of course that means e dot equals e naught to the power of f prime of x1 t will just go to infinity. So yes, x t minus x will not go to 0. It's unstable. And we can see in this diagram right here what I was trying to talk about. So where x1 is the equilibrium point. For greater than 0, we start here, initial condition, goes off to infinity. But less than 0, it will go towards x1 as t increases, obviously, because time is obviously increasing. So now we will look at bifurcations for one variable, as we already have considered about stability. So therefore, consider such an equation, x dot equals x squared minus a quadratic equation. So setting this bit of f of x equals to 0, we can just find from the quadratic equation that the equilibrium points are just plus or minus square root of a. And of course, we have to make sure a is greater than or equal to 0 because we want to look at the reals, for example. We're not considering a complex at the moment. So yes, they only exist for a greater than or equal to 0. So stability of equilibrium points, as what we've seen earlier, you have to derive this area, f of dash of x, of course, what we've seen earlier. So then f dash of x here is just 2x. And if you sub in one of the equilibrium points, which is positive square root a, then it's just 2 square root a, assuming that it's greater than, assuming a is greater than 0, it is greater than 0, therefore it's unstable. And if you put the negative square root, then therefore an a is greater than 0, then f prime of that value is less than 0, therefore it's stable. So at a equals 0, in fact, we would have a bifurcation value because, of course, f prime of x would be exactly the same for both, which is also known as a fold bifurcation. Of course, if a is less than 0, no equilibrium points because, first of all, we are only talking about the reals, so no equilibrium points. And 2 equilibrium points when a is greater than 0. And in case of 2D flows, which we will go on later on, talk about later on, this kind of bifurcation is also known as a saddle node bifurcation. We will see why we are talking about this. So therefore, the formal definition of a bifurcation is given below. And if you want to see a diagram of fold bifurcation, we will talk about this later on in this presentation. So this is the formal definitions. So first, before we go straight to bifurcation value, we have to realize that if we have two variables right here, x dot equals f of x and y dot equals g of y, we need to know that they are topologically equivalent. Basically means there's a smooth transition from x dot to, let's say, h of y, such that all orbits of solutions of this transform into solutions of this, keeping the same direction of dynamics. Like, let's say if g of y has something like this, but then you can rewrite x as a form of h of y, not exactly the same, but there will exist like an isomorphism to h of y. So structurally stable, x dot equals f of x times c, where c, we have to realize that c is a parameter. Please keep in mind c is a parameter and not a variable. We will talk about that later on, if it's a variable. C is called structurally stable if at c for c star, which is the parameter value, if f of xc is topologically equivalent to x dot of f x at c star for all values in the vicinity or nearby of that parameter star value. Now, bifurcation value, which is the value of c which is equal to that, such that the equation now is not structurally stable and is called a bifurcation value. So therefore, we will now look at, let's say, like another basically definition. So let x dot equals f of x times c have an equilibrium point at x star and with the parameter.
Hi, Hardik.
Sorry, yes?
Can you explain a bit more in detail the last three definitions, if possible? Thank you.
Okay. So I'm just wondering which bit are you more confused about, all three or?
If you could say a few words about the three of them, that would be better.
Okay. So basically, when I think I was talking about topologically equivalent, so like since that also orbits are solutions, I'm not sure if you can draw on Zoom or if you have like a pen option, because it could have been a bit helpful to explain topologically equivalent right here. Do you know if that's possible?
I'm not sure what you can open the whiteboard if you want. That's another option. You can start sharing the whiteboard. But I mean, you can come to the detail at the end of the talk. So it's okay. You can move on.
Okay, yeah, no worries. So yes, I was about to start with an example right here, where x dot equals f of x is c has an equilibrium point at x equals x star and c equals c star, where of course it equals to 0, because by definition of equilibrium point. So let's say we can find another variable y at a parameter a such that y dot is equal to a different value, different function f of ya has an equilibrium point at 0, 0. So I think I was actually going to get into like the topologically equivalent, because the fact that if we have one equilibrium point at x star c star, then we can shift, let's say like when we talk about topologically equivalence, that's why I wanted to show a diagram that we can shift the system to show like we can shift an equilibrium point to 0, 0, because that if it's topologically equivalent, then the system of equations will be exactly the same, but they'll just be placed at a different point. So that's why like we can shift using y and another parameter such that it has an equilibrium point now at the origin. So does this does it help you understand a bit when you mean by topologically equivalent? So yeah, indeed, after substitution, y equals x minus x star and a equals c minus c star. Sorry. So therefore, we get x dot equals dx by dt equals dy plus x star, because for topological equivalence, when we can just shift the whole system into y and a, therefore it'll just equal to dy by dt, which is equal to y dot, and of course we could just rewrite this f equals y of a. So it's just the new system, f equals y of a, just a shift of basically topological equivalence. So now the equilibrium point is now 0, 0. So therefore, f of 0, 0 would also equal 0 as well. And the origin, we can therefore confirm that it's just an equilibrium point. We normally do this using the the knowledge of topologically equivalent, so that it will be very easy to use our analysis, like if we want to use linear analysis. So that x dot equals, let's say, has another equilibrium point, and therefore, right. So now it's x dot equals has an equilibrium point now at 0, 0, and f the derivative at x is not equal to 0, meaning first f of x is the first derivative of x with respect to x. Then in the neighborhood of c equals 0, we can have an equilibrium point of the same stability. So coming to the proof, consider the parameter c is not 0, but it's very small. So from a linear Taylor approximation, we can use that x dot equals f of x to c, which is just the f of 0 at equilibrium point, first derivative of x times x, plus first derivative of c times c, and therefore since this is 0, we can just get these two terms. So an equilibrium point shift happens when we change the parameter c, which is just also given as f prime of x, obviously at 0, 0, which just equals to x is equal to minus f of c over f of x times c. So therefore, the stability equilibrium point x of c is given by this right here. So now we assume that this is at the equilibrium point 0, 0 is less than 0. Then, of course, this value f, the x derivative, is less than 0 for all values of x and c in the neighborhood of 0, 0, and therefore the value of x as c, which is properly defined, is stable. Similarly, if it's greater than 0, then the equilibrium point here now is unstable. And of course, we defined c to be a very small parameter change. So therefore, we will introduce another definition called a hyperbolic equilibrium point. X star is when an equilibrium point is where the derivative at x star is now not equal to 0. And we have a theorem saying that if x dot equals f of x to c as a finite number of hyperbolic equilibria, then it is structurally stable. This is, of course, illustrated by Bifurcation diagrams on the figure below for a single hyperbolic equilibrium. So what bifurcation diagrams actually do is just they show the location of equilibria depending upon the C parameter. So this panel here shows that the equilibrium point at 0, 0, where we know that the derivative is greater than 0 because it's positive, 0, 0, for example, if it's less than 0, this diagram side does not show that, but it will shift along this line in a linear approximation, but stay stable when this is changed. So what this solid line means is that it is stable, but the shift, which is according to the parameter c, will happen only along this line only, and the system will stay in equilibrium because it's staying here. Meanwhile, on the right, we show that now it's greater than 0. But therefore, even although C stays changed, the whole equilibrium system will be same, but it will not go like according to this line. It will probably diverge somewhere else because it's unstable. So now we will look at two types of classifications of bifurcations. There are three types, one called fold bifurcation, one called transcritical bifurcation, and one called pitchfork bifurcation. We will talk about only two of three because of time constraints. So consider the one-dimensional map x dot equals f of x as c. So let therefore 0, 0 be an isolated equilibrium point, and let the derivative of x at the equilibrium point is now 0. So this means that this equilibrium point is therefore non-hyperbolic as it's equal to 0, and therefore bifurcations can take place at this point. So let's consider quadratic approximation of our equation at 0, 0. Therefore, we just look at the Taylor approximation into its quadratic terms. And therefore, since 0, 0 is non-hyperbolic, therefore the first term, f of 0, 0, because it's equilibrium, this will equal 0. And this value, as we set to equal 0, will equal 0. So therefore, we can just only consider these four terms only. X dot is equal to f of c 0, 0, plus f of double derivative of x divided by 2 times x squared, plus the derivative according to x and c, 0, 0 times xc, and double derivative fcc divided by 2 is 0, 0 times c squared. So for simplicity, we will just rename these four bits as A, B, C, and D, just for simplicity, the constants. So now consider where this is not equal 0 and this is also not equal 0. So therefore, the previous equation is just rewritten as this. So therefore, since it just squares in terms of x and c only, after completing the squares, we can get the following, which is AC plus b of x plus d over 2b times c all squared plus e minus d all squared divided by 4b times c squared. You can work it out on a piece of paper if you're unsure. And then take into account that c is obviously super small, and obviously c squared will be even smaller. So we assume that we can remove this. It's very, very close to 0, just removing this term. So therefore, we can also substitute just this with the x tilde, this whole thing with just a new variable, and then getting rid of the x tilde just for simplification. Therefore, we get AC equals AC x dot equals AC plus bx squared. The reason we can do this, if anyone is unsure, it goes back to, again, topological equivalence. You are not moving, you are not changing the entire system. So therefore, we will make substitutions which can be slightly different depending on A and B only. And then after, let's say, substitutions, we will have a new parameter x tilde and c tilde, such that we know that x tilde will be increasing if x is increasing, c tilde is increasing when c is increasing, and therefore a very simple case we will look at, and just one of them. So if a is greater than 0 and b is greater than 0, so we're just using substitutions, x tilde equals bx and c tilde equals abc, transfers this equation into a simplification of a normal form where x dot is equal to c plus x squared after just removing the tildes. So we can make these types of substitutions. So therefore, and equilibrium points are, of course, roots of this equation right here, c plus x squared equals 0. So yeah, we have simplified the equation to make it look much more simpler to analyze. Which, of course, we find that they are plus or minus square root of c, and they exist for real numbers if c is less than 0. To analyze the stability of equilibria, we of course differentiate, which is 2x, and evaluate at plus the square root of minus c and minus the square root of minus c. Therefore, obviously for x1, since it's positive, therefore it's greater than 0, unstable, and the minus square root of c value less than 0, therefore this is stable. And then a bifurcation diagram can be seen later on in panel A if we want to see what a fold bifurcation looks like. So for A and C of arbitrary signs, of course, we can just therefore simplify to get something like this. And then take into account that A divided by modulo A is just plus or minus 1, and same thing with B. Therefore, for other cases, we can just write x dot equals plus or minus c plus or minus x squared. We have just already looked at one case. You can also do this as an exercise and look at the other cases for yourself, for if one is positive, the other negative, other negative, one positive, one negative, one negative. So therefore, yes, there are 4 possibilities. And then the conditions, of course, for fold bifurcation to take place is that f of c is not 0 and f of double prime of x is also not 0. And these conditions are called non-degeneracy for fold bifurcation. And a signature of fold bifurcation is which one is stable and the other is unstable. So therefore, if you can see on the next diagram, where cases of course, for the others. Or then if you want to look at the diagram now, which I've just talked about the signature ones, where let's say, where minus C, where the minus bit is a stable, unstable. Here is unstable, here's stable, here's unstable, where C is basically positive side for minus x squared, unstable, stable, and stable, unstable. Bifurcation case for all four. So now we will look at a different type of bifurcation called a transcritical bifurcation. Of course, essential that fc equals not zero and f of double x is not zero. So these are non-degeneracy cases for fold bifurcation. However, if they are broken now, then we of course get many different types of bifurcations. So we have derived earlier in the earlier quadratic approximation that a equals 0. Then, therefore, it will transfer to something like this. If this is non-zero and this is non-zero, therefore we have bifurcation, a transcritical bifurcation. So simple cases when e is equal to 0, let's say assume that is 0, then therefore it simplifies to this. And using substitutions for topological equivalence, where x is equal to x tilde over b, and c is equal to c tilde over modulus of d, we therefore get something like this, in which, of course, we can get the four cases again. And just removing the tilde for simplicity, we can write it like this. Equaling this to 0 and factorizing, we therefore find the solutions will be x equals 0 and c will be plus or minus c. Therefore, we can see the bifurcation diagram on the next slide. So therefore, for this one, where x dot is equal to x squared plus xc, 0 and c depends. So obviously, when c is negative, this fits all unstable. Now c is now positive. However, this is now unstable, but the x values are stable, even though the equilibrium point, the bifurcation is actually at 0. Likewise, for this equation right here, it is similar to this. Positive c, we know that the x is stable, c is unstable, and on this diagram, on this parameter, it is now unstable. And similar to this, dotted line unstable, unstable, stable going down. And then, so this is how bifurcation diagrams for transcritical bifurcations look like. The pitchfork bifurcation, if you just want to have an example, we'll have something along a line here, and a line here, and another here. So it's like a fold and a transcritical both combined. But I think we're running out of time, so we won't go over this too much. So now we move on to two variable systems now, where stationary solutions are defined by the conditions x dot equals 0 and y dot equals 0, or of course, just f of x of y and g of x and y are equal to 0. So when they're equal to 0 at, let's say, x star, y star, they're called equilibrium or stationary points. Formal definition is very similar for one variable. So we've just, instead of x star, y star, we've just been capital X and capital Y. So this is asymptotically stable if there exists an epsilon such that x naught minus x plus y naught minus y all squared is less than delta squared. Then, of course, xt converges to x, yt converges to y when t converges to infinity. And x naught and y naught are initial conditions. The second definition, which is a stronger definition for stability, which is Lyapunov stable, is such that for all epsilon, there exists a delta such that now this is also true, which for asymptotically stable, then x of t minus x all squared plus yt minus y all squared is less than epsilon squared. It is not diverging at all. So now we consider a simple linear system. X dot equals a11x plus a12y, y dot equals a21x plus a22y. The equilibrium point satisfies this system now, where x dot equals a11x plus a212y, y dot equals a21x plus a22y equals 0. Thus, therefore, obviously, we can just check that x equals y equals 0 is just an equilibrium point. But since we already have a two-variable system, we can just create a matrix A and a vector u, where A consists all the parameters and u is the vector of x and y, such that now u dot is equal to A times u. So we, of course, have seen previously for the one variable solutions in terms of u for each individual variable are very similar. They're just C1, which is C1 B1 e to the power lambda 1t plus C2 B2 e to the power lambda 2t, where B1 and lambda 1 is the eigensolution, where B1 is an eigenvector and lambda 1 is one eigenvalue for one of them, and the other eigenvalue lambda 2, as we will find that if you find the determinant of A, therefore you will have a quadratic in terms of lambda, and there will be two lambdas, obviously. So B2 lambda 2 is the other eigensolution for this matrix. And C1, C2 are just the constants defined by the initial conditions. So therefore, introducing, let's say, B, which is just consists the eigenvectors, and making the following solution, u equals b times v, which is another vector. Then therefore u dot equals a times u. Substitute this, which will be a times b times v. So what is this product AB now? So A is, which is just A, basically the matrix times the eigenvectors. And of course, you can distribute each individual one. AB1 will of course equal lambda 1 B1 because eigenvectors and eigenvalue definitions. So AB2 will equal lambda 2 B2, which of course, this should be written the other way around. Apologies for that. B1, B2 should be on the right side. A1, A22, 21, A2, which is just equal to B dot of D. And D is a diagonal matrix. So therefore, B dot V dot is equal to B dot V times V. And then, of course, we can cancel B on both sides. So therefore, V dot is equal to D times V, which therefore V dot V2 is equal to lambda 1, 0, 0, lambda 2. D is the diagonal matrix consisting of the two eigenvalues, and V1, V2 is just a new, basically, basis, we can say, of new vectors. And of course, like earlier, what we try to do is just simplify so that analysis can be done much easier. So therefore, the solutions of V1 dot and V2 dot are given looking at each individual line. V1 dot equals lambda 1 V1, which therefore would just equal V1 dot e to the power lambda 1 t. V dot 2 lambda 2 of V2, which will just be V2 of t equals V2 naught e to the power lambda 2t. So now rewriting this back into terms of u, therefore x of y equals b times v1 v2. We know what b1 is, b2 is, we know what v1 is, we know what v2 is. So therefore, we have now the full equation which we can find in terms of u, where v1 not b1, where v1 not and v2 not are effectively the initial conditions right here, the seeds that we were talking about. So there are many types of equilibrium points for eigenvalues lambda 1 and lambda 2. So if they are real, then the type of equilibrium 0, 0 can be defined according to the following four cases. Case 1, lambda 1 is less than 0, lambda 2 are both less than 0. Phase trajectories tend to the equilibrium point, 0, 0, and this is called a stable node or a sink. If one is less than 0 and another one is greater than 0, no convergence, the equilibrium point is unstable and called a saddle. Both greater than 0, no convergence, and therefore the equilibrium point is now completely unstable and is called a saddle node or a source. It will be much easier if you can see the Poincare diagram, which we will show later on. So now it's a bit difficult when you consider if they're both equal. So if matrix A has two linearly independent eigenvectors, and however we still have two equal eigenvalues, then the node right here is called a star, because it goes to one point. But they obviously are going away, like a star. It looks like a star. And this one, subcase 2. Let's say we only have one linearly independent eigenvector. Then the value for u, c1 beta value et plus c2 tan bt, we note that because b2 can be formed based upon b, but they still have to have two different ones. So therefore equals where b dot is equal to I minus lambda I times b is called an improper node or a degenerative sink or source. So these two, we're just looking at a star and a degenerative sink, where it looks like it's going together. If it's sink, it'll go towards. Both cases are sources, they're going away. And yes, it's called a degenerate source. So these, and when it's a star, trajectories are not curved, and then stable if lambda is less than 0, unstable if they go away. And then similarly, the arrows are pointing away, which we assume that the lambda is greater than 0. So now we can even consider complex eigenvalues. Lambda 1, lambda 2 equals alpha plus or minus I beta, where b1, b2 are just now eigenvectors in terms of i's, br, which is the real bit, and the imaginary bit of the eigenvector. So we call that the solution, whereas we find earlier b1, b2, and using Euler's formula, where let's say e to the power of I something can equal it cos something plus I sine of something. Therefore, this should be plus I sine beta t. And then what we can see right here after substitution, therefore c tilde br cos of t minus the sine of t, which is of course this right here, the imaginary part times this. And then we are only looking at the reals, for example. Looking at the imaginary part is very similar, but we disregard all of this. Where C2BR sine BFT and minus I cos. So therefore, the real part of solution can be represented as this. Cos beta, sine beta, minus sine cos, C1, C2, we're just replacements of C1 and C2. So in case of complex eigenvalues, the equilibrium is defined according to 3 cases. If alpha right here is now less than 0, it's a stable focus or spiral sink. Greater than 0, unstable or spiral source. And if it's equal to 0, it's a center. So now, as a type of equilibrium is of course defined by the eigenvalues of a matrix A we have described much earlier, we can of course state the conditions of equilibria just in terms of a matrix only A. Indeed, eigenvalues are roots of this characteristic equation, lambda squared minus trace plus the determinant equals 0. You can do an exercise and look for it yourself. And thus, therefore, lambda 1 and 2, which of course we defined by this from the quadratic formula. And of course, eigenvalues will be real if trace squared minus 4 determinant A, which is the determinant, is of course positive, which this is just saying that the discriminant is positive. So therefore, it is easy to see that both real eigenvalues can be negative if trace is less than 0 and determinant greater than 0. If both less than 0, we have two eigenvalues of opposite sign. Equilibrium is a saddle. One is greater than 0. Oh, sorry, both are greater than 0. And we have a positive discriminant. Then eigenvalues are real and positive unstable node. So therefore, if we have a negative discriminant, then therefore complex eigenvalues and spiral, and then the sign of the real is determined for the sign of trace. For if trace is greater than 0, unstable spiral, less than 0, stable spiral, and if it's equal to 0, the point is the center. So everything what I have just talked about and just mentioned is, okay, we can see it right here. The trace and determinant. Negative trace, positive determinant, you can find eigenvalues are obviously negative, obviously a positive discriminant, sink, negative discriminant, spiral, complex eigenvalues, complex here as well, spiral source, real eigenvalues. Therefore, it is just trace, but then both lambdas are positive, therefore unstable. This is a center when, of course, the trace is equal to 0. This is obviously the line where discriminant is equal to 0. And anything below, which we find, which would obviously mean one eigenvalue negative, the other positive. Anything below this line is just a saddle. Line of stable and line of unstable. And of course, there are all different dynamical regions. So if we cross from one to another, we would have a bifurcation. So you can consider these lines as bifurcation lines for simplicity. So now we're looking at consider a nonlinear system case, where now f of x of y and g of x of y are not just linear, but they can also consider squares or quadratics. Therefore, they divide the phase space into domains where flows have different directions. Of course, we can know this is where we can find the direction field. We also know that equilibrium points are found as roots of this system. So therefore, to determine the stability and type of equilibrium points, we need to linearize the system and find eigenvalues using Taylor expansion up to first order. So if this is an equilibrium point, then just obviously adding a little perturbation with small values, let's say epsilon and delta are super small. Using first order expansion, we can get this. Obviously, this is equal to 0 as this is an equilibrium point. So this is what you get for f, and similarly what you get for g as well. Of course, we know that x dot is equal to epsilon dot, y dot is equal to delta dot, since the difference of two variables are just given by constant x and y. Thus, therefore, linearization of original system at the equilibrium point xy results to something like this, of a much simpler system. Therefore, we can just also write this as a Jacobian along with the matrix fx dot xy, fy prime, xy g of x prime, of xi and g of y prime of x and y. So now, the type of equilibrium at the equilibrium point is defined by the eigenvalues of this Jacobian matrix. Same way as we find for equilibrium at 0, 0 for linear system. So linearization allows to catch the dynamics in a close vicinity of the equilibria. Global picture can be obtained by consideration of stable and unstable manifolds of saddles, similar to what we've discussed considering nonlinear maps. Stable manifolds of saddle points separate domains of attraction are stable nodes. as stable nodes are always located on unstable manifolds when unstable nodes unstable manifolds. So now that we've seen a long introductory stuff, we can just look at a short, small biological application. So in the natural world, we can see patterns formed on many animals, like such as stripes on zebras, spots on leopards. And normally these pattern formation happens at early stages at morphogenesis. Yes, that these patterns can be related to mathematics, as we call them as Turing patterns. So Turing patterns are such patterns formed as a result of small perturbation around the stable point, and this causes the system to leave the equilibrium state and undergo one of the bifurcations. It could be a fold, could be a transcritical, can be a pitchfork bifurcations. Once the bifurcation has happened, however, the system does not return to equilibrium but stays in a new state. And there are many such models to represent pattern formation. So we'll just, for this purpose of the presentation, we'll just use the Greer-Meinhardt model, where A and H are two variables. One is the activator chemical and one's the inhibitor chemical. Of course, this inhibits the growth of A, as we can see here. We know that since this is a PDE now, since we are also considering space as well, the chemicals not only grow in time, but they move around in space in order to form a pattern. So dA and dH are diffusion coefficients. So this is a nonlinear, and this is also autonomous because we do not have an explicitance of time. Of course, when we set diffusion equal to 0, we will get the ODE as what we've seen earlier, which will just be a nonlinear first order ODE. And then we can find stability points and then determine a Jacobian matrix, find your eigenvalues, and determine the stability of the systems. But of course, once we add that spatial coordinates right here, and let's say these are different values of diffusion, non-zero, then therefore, since it's in PD, we have to, of course, consider e to the power ikx as part of a solution apart from e to the power lambda t. This is for PDEs, and therefore, for bifurcation analysis, we can tell that if the system will change or not. And the critical condition is depending upon dA and dH. A nonlinear bifurcation can therefore, because we've already seen for the purpose of the presentation, we only look at linear bifurcation analysis. In the future, we can look at nonlinear bifurcation analysis and then therefore determine the amplitude and then therefore whether spots or stripes appear and by how much and how far are they. So yeah, thank you for the talk. That's pretty much all I have to say. So.
Thank you very much, Hardik, for this interesting talk. So yeah, now we'll take questions if there are any questions from the audience.